Welcome. Today we're going to be studying rates of change. We're going to be studying how rates of increase and rate of decrease can interact together to describe the amount of something. We're also going to be looking at how those rates of change affect the rate of change in the height and other features of the shape. We'll be working what I'm calling the sand removal delivery problem. Let's read through it together. For 0 less than or equal to t less than or equal to 6 hours, sand is poured into a cone at a rate of P of t equals 10t over t squared plus 4 cubic meters per hour. Beginning at t equals 4, and from 4 less than or equal to t less than or equal to 6, sand is removed from the tip of the cone at a rate of 4 arc sine 3 over 2t. Again, that's in cubic meters per hour. So we don't know the true value for what s is. Let's define a function s to be the total volume in the sand. So we'll make that the function that is what's being described here. Now, we don't actually know the values for s because all we have is their rates. And it would be rather difficult to do so since this equation here might be difficult to integrate. And we don't need to yet. So let's take a look at our first problem, our first section for this problem. All right, part A is telling us that given that at t equals 2.5 hours, the pile has 5 cubic meters of sand, use a linear approximation to predict the amount of sand at 3 hours. So a linear approximation is a really useful tool when we don't have the equation. So just by way of example, let's say that we had a curve like this, and we had this curve, but we didn't know the real true equation. Well, if we were able to get a slope of a tangent line, and we knew that point's x and y coordinate, we could generate a tangent line and then use that tangent line to estimate values of the curve in the neighborhood around the point of tangency. As you can see, when we go further from the point of tangency, it gets less and less accurate, though, both to the right and to the left. But it's still a really useful tool. So let's try that. Let's try and get a linear approximation. A linear approximation, this just simply means tangent line. So first of all, let's try and describe s prime of t. Well, this question threw us a bit of a curveball because we've got more than one rate to consider. We've got this rate P of t, which is the increase in sand, and then we got this R of t, which is the decrease, but R of t doesn't kick in until time 4. So s prime of t really needs a piecewise defined function, where from time 0 up to 4, we need to be using just P of t. So I'll put 10t over t squared plus 4 there. All right, well then after that time, we are going to have a different value for s prime of t, because after that time, we need to incorporate both equations, because now we're both adding at the rate 10t over t squared plus 4, but we're also taking away at a rate of 4 times the arc sine of 3 over 2t. but that is going to be only used after 4 hours. So that's going to be from 4 less than t less than or equal to 6. Now, what exactly happens at exactly the time t equals 4 is a little bit complicated, because this function may or may not actually be continuous, but let's not worry about that issue unless we have to. Okay, so we need to find t at 2.5. Well, for 2.5, I think we can agree that we just need to use this top equation, this top portion here. So let's go ahead and evaluate that. So I'll simply find s prime of 2.5 by evaluating 10 times it over its squared plus 4. And we'll just simply use a calculator for that. Okay, and we get 2.439. So that is the rate in cubic feet per hour that the sand pile is increasing. So a linear approximation, if we use this equation here, y minus y1 equals slope times x minus x1. And I'm simply just going to move the y1 over to the other side. And we get this idea that the y-coordinate, the amount of sand that we have right now, this y-coordinate, the amount of sand we have right now plus the rate of change in the sand times the amount of change in the time will give us the amount of sand that we have in the future, or at least an estimate of it. So that tangent line is y is equal to y1 was 5, because there's 5 cubic meters of sand at that time. The rate of change is 2.439. And our x coordinate that we are using is 2.5. Okay, now that we have that equation, we can simply evaluate what amount there must be at time 3 by plugging 3 into our equation. So we're going to say it's approximately. We're just going to plug 3 in right here to our tangent line equation. And again, we'll let the calculator do that for us. We get 6.220, or somewhere around there. And that's in cubic feet. All right, so that's our first part of the question. We've got that we were able to use a linear approximation to predict the amount of sand that is there at that time. Okay, let's go to our next part. Okay, bear with me just a second. A little bit of technical difficulties here. All right, here we go. All right, part B. Determine S double prime of 2.5. Based on this result is the prediction for part A an overestimate or an underestimate of the true amount of sand in the pile at this time. Okay, so we already know that S prime of 2.5 is just this right here with 2.5 evaluated. We got S prime 2.5 right here. So let's find S double prime. I'll go back to blue for that. And so S double prime, not on pin, there we go. So as long as we're in the range of 0 to 4, we can just take the derivative of this equation here, which is 10 times t squared plus 4 minus 10t times the derivative of the bottom would be 2t all over the bottom squared. And we can also just have our calculator evaluate a numeric derivative here. And so there we go. So that is S double prime as long as t is between these values. Okay, so let's go ahead and evaluate S double prime at 2.5. And we get negative 0.214. So that's the rate of change of the rate of change of the sand pile. It tells me that the function S is concave down at this moment. So let's take a look at this graphically. We could think about it in terms of velocity or acceleration, but I kind of just prefer to think about this graphically. If at 2.5, whatever this equation S is, and we don't know it, we do know that it was increasing because S prime at 2.5 was positive, but we know that it's concave down. So that means that it's kind of shaped, kind of like this, increasing but concave down. So it's increasing but at a decreasing rate of increase. So that tangent line that we found at 2.5, well, it's on the outside of the curve because the curve is concave down. So that tells me that whether we move to the right, which we did to go from time 2.5 to time 3, or we go to the left, either way, we're going to get an overestimate. So we know that we overestimated our value of S of 3. So, or in other words, we could say that S of 3 is less than or equal to the value we got earlier. We could do some more kind of work maybe to get a lower bound so we can make our estimate a little bit more exact. But that's really useful. We have an estimate and we know that our estimate is, going to be too high. All right, let's move on to the next part. Okay, bring this question in here. All right. Is there a time when the volume of sand in the pile changes from increasing to decreasing? Okay, so our function S, again, we can draw it here. We have this function S, and that's going to be the volume of sand. And we've discussed that we don't know that equation, and it might be quite difficult to get. But if it changes from increasing to decreasing, what that means is that we had a time when the rate of change of it was 0. So we're looking for a horizontal tangent line. Well, remember earlier we found the equation that we needed. We had that right here. And let's go ahead and use that equation again. So I'll just move it down here. There we go. All right, so we have what we have here is we have this equation here. And now this is the rate of increase. And this is always going to be positive for any t value because between 0 and 4. Because if you plug in a number like any number between 1 and 4, the top 10t is positive, t squared plus 4 is always positive. So that's always positive. The only way we could all of a sudden have the derivative equal 0 would have to be using this bottom portion here. Yeah, this is what has to happen. So it has to happen between 4 and 6. So what we really need to do is we need to solve this equation here equal to 0. And what I would do there is I'm simply going to graph it. I'm going to graph this and look at the graph from 4 to 6. See if we can't get any kind of zeros in that range. So we'll just go there and graph it. Press the wrong thing there. Okay, so here's an image of the graph. And I think you can see that there's not a point from 4 to 6 where that's going to happen because the derivative is never 0 there. It's 0 over here, but that's before we're using the time t equals 4. So yeah, there's not going to be a time where it switches. It definitely is going to be decelerating, but it's not going to be 0 at any time. So we can just say no to that one. Yeah, no. And our justification is simply that the derivative, s prime of t is, well, it's continuous and it's greater than 0 on the interval from all the way from 0 to 6. So that's not going to happen. All right, let's take a look at our last section. Let me just get some more room here. I think we have one more question to do. Okay. All right, there's our last portion here. Let me just give us a little bit more room here to work. All right, we have the sand is delivered into the top of a conical vessel shown below. It funnels out of the bottom. We're going to find the rate of change in the height of the conical volume of sand at time 5 hours. All right, well, let's start with the volume formula for a cone. So the volume formula 1/3 pi r squared h. And we can see by similar triangles that this r is always half of the h. And we're looking for a rate of change in height, so I'm going to do a substitution, and I'm going to try and get everything in terms of h. So I'll make that 1/3, and then we're going to call this h over 2 squared times h. Okay, and so that becomes, what is that going to become? That's going to tell me that volume is 1/3 pi, try that again, pi h to the third over 2 squared is 4, so we're just going to make this 1/12. 4 times 3, 12. Okay, so there we have it. So when we take the derivative, the rate of change in the volume, dV dt, which we have an equation for, is equal to, bring down the 3, and I get 1/4 pi h squared dH dt. Okay. dV dt at this time, at time t equals 5, just means we need to evaluate s prime of 5. Which is 0.505. All right, so then we were not going to be able to get an actual numeric value here, but if we divide all this and multiply it, and I'm not going to simplify it, but I'll just say 4 times 0.505 all over pi times the height squared, then we get dH dt. Now, if we could find the volume, and we could, going back and using previous information about the problem, they told us the volume at a specific time, we could use a numeric integration. We could go through and find h, but we'll save that for another lesson. So we'll just stop there.